So recall that the dot product, which we define in section 3.2, is also sometimes referred to as the scalar product. And the reason is for that is because no matter which vectors you plug into it, you always get a scalar back as the result. And so far, we don't have a way to multiply vectors that results in now another vector coming back as the answer. But in this section, that's going to change. We're going to define something called the cross product, which will multiply two vectors and give us back another vector as the result. Now, the catch is this only works in R3. Okay, but if you do have two vectors in R3, they can be absolutely anything at all as long as they each have 3 coordinates. So I've labeled U to have the coordinates U1, U2, and U3, and then V to have the coordinates V1, V2, and V3. You know, just following the usual convention. So in this situation, we can define the cross product of the vectors U and V as follows. So first of all, the notation is like that. We just write it out as, we write the literal multiplication symbol in between the two vectors that you would probably be used to seeing back from elementary school, right? As opposed to the dot. We'd use a solid dot if we're doing the dot product, but if we're doing the cross product, we write, well, it's kind of like a cross, right? So that's the reason for the notation. And what it's actually defined to be, it's actually a little bit of a mess, but nonetheless, this is the definition. The first coordinate is actually, what we do is we take U2 and V3 and multiply them. And then we subtract U3 times V2. And that's all just the very first coordinate. So that's the first coordinate, right? And now for the second coordinate, we take U3 and V1, and then we subtract the product of U1 and V3. And then finally, the third coordinate, we take U1 and V2, and then we subtract U2 and V1. Now, this is, well, I mean, this is technically the definition, but you might already be thinking, wow, do you have to memorize this? And, well, like, technically no, but it would be nice to not have to constantly look up the formula every time you want to compute a cross product, right? Because it would be tedious. But at the same time, memorizing this doesn't exactly look like really the most pleasant experience either. So the good news is, though, there's a nice trick to memorize it that doesn't involve writing out all these coordinates of the original vectors u and v. Well, you still need to write them out, but you don't need to write them out in quite this long of a fashion. So that's what this next remark is for. So instead of remembering this formula, it's easier to calculate the cross product using the following determinant. Now I put the word determinant in quotation marks because while it looks like a determinant, technically it's not really a determinant. And you'll see what I mean in a moment. But anyway, that doesn't matter. The important part is this helps you memorize the definition of cross product. So here's how it works. If you want to compute the cross product of u and v, well, you just consider the following matrix. And if you could see my face, you'd see me putting quotation marks around the word matrix because there's something weird about this matrix, although technically it's still a matrix, but there is something weird about it. The first row is actually not going to consist of numbers, it's going to consist of vectors. So the first row is going to be written like this, and I'm going to say exactly what these letters mean in a moment. But I'm actually writing vectors for the top 3 entries, I, J, and K. And I'll tell you what those are in just a moment, but for now, just know that these are vectors. And then the second row is going to be exactly the coordinates of the vector u that were given up here, and then the third row is going to be the coordinates of v that were given up here. So this is what the rest of it's going to look like. U1, U2, U3, and V1, V2, and V3. So that is what you want, okay? But the question remains, what are these vectors up here? Well, these are actually just nicknames for the standard basis vectors in R3. So, but let's add that in now. So I'll formally say what those are, where I, the vector I, is just the standard basis vector E1 in R3. So it's just the vector 1, 0, 0. And then J is the standard basis vector E2, which has coordinates 0, 1, 0. And then K, if you had to make a guess, you'd probably guess the standard basis vector E3 at this stage, right? And that would be correct. So it's going to be 0, 0, 1. So those 3 vectors I, j, and k are defined by these rules. Why don't we just write E1, E2, E3 up on the top row? It just seems to be historically the case that whenever I see this done, this is always what is done. So I'm going to go with the normal convention. And there's lots of fields where they typically will use I, j, and k for the standard basis vectors in R3. So it's just common. That's a common convention, so we're just going to go along with it. Okay, so, but this, you wouldn't write this out every time, right? This is just something you kind of internalize. I, j, and k are just the standard basis vectors in R3, but this is really what we want to put a box around. This is the important part, because now this is a lot easier to remember than all of this, right? Just put I, j, k on the top row. Second row is your the coordinates of your first vector. The third row is the coordinates of your second vector. So this is a much more convenient rule to work with. Why did I put the word determinant in quotation marks? Well, because this really isn't a 3 by 3 matrix of real numbers, because the top row consists of vectors. So it's kind of, well, it's kind of weird to think of it as a determinant, but as we'll see in a moment, it actually works very well. And the last little bit here that I didn't quite finish the sentence, right? How does it work here? Instead of remembering the formula up here, it is easier to calculate the cross product of u and v using the following determinant that I've written down here. And then at the very end, we finish the sentence using cofactor expansion along the first row. So I'll show you what I mean by that by computing an example. So we've got a vector u, which is 1, 2, negative 2, and a vector v, which is 3, 0, 1, and we're asked to compute the cross product. So we'll just go ahead and use this rule up here. Okay, so let's just start by going u cross v. I'm not sure how much room I'm going to need, so I want to make sure I start all the way over on the left-hand side of the page, but by definition, it's just going to be, well, by definition, technically we would have to use this rule, but using the shortcut, really it's not a shortcut, it's just a memory trick that helps you not have to constantly refer to this formula. But so you might as well take this to be the definition. There's nothing wrong with that. And sometimes I'll accidentally call this the definition because I have just come to have that habit of thinking of this as the definition, but technically this is the definition up here. But let's use this rule. So we're going to form sorry to keep sliding around, we're going to form a 3 by 3 matrix. The first row is going to be the vectors I, j, and k, right? And then our second row is going to be the coordinates of this vector u. So we're going to have 1, 2, and negative 2. And then the third row is going to be the coordinates of the vector v, which is given over here as 3, 0, 1. Okay, and then we're going to do cofactor expansion along the first row. So we're really just taking a determinant here, right? So the first position here, the I, well, that's a positive position if I think about the plus and minus symbols, the plus and minus signs on a 3 by 3 matrix. So we're going to have positive I, and then we're going to multiply by the determinant of this 2 by 2 matrix. So 2 times 1 is 2. Negative 2 times 0 is 0. So we really just got 2 minus 0. Okay, then now we're going to move on to the j. So now we're going to switch signs. It's going to be a negative term. So we're going to say minus the vector j. And then now we're going to take the determinant of what is left if you delete the row and column that are occupied by the j here. So delete this row and this column, and you've got the determinant of the 2 by 2 matrix, 1, negative 2, 3, and 1. So 1 times 1 is 1. Negative 2 times 3 is negative 6. So we've got minus negative 6, and then that is our second term. And then our last term, we're going to go plus the vector k, and then the determinant now is going to be of this 2 by 2 matrix. So 1 times 0 is going to be 0, and then 2 times 3 is 6, and we're just going to subtract that, and we get 0 minus 6. So that is what we get. So now let's just clean everything up. So what's this one going to be? This is 2, right? 2 minus 0 is just 2. So the first term is just 2 times the vector I. And what do we have over here? Well, I guess we just keep it simple. Copy the negative sign down first, and let's just work this out. So 1 minus negative 6 is positive 7, so we got a 7 there. And then lastly here we've got plus k times negative 6. So really that's just going to be negative 6 times the vector k. And I've kind of left this middle term still with a little bit left to work out because we spent this whole step just worrying about that. But now that you have minus j times 7, we can just write that as, slide this up just a bit, you can just write that as 2i minus 7j minus 6k. So that's actually a perfectly fine way to leave the answer, because that in the ijk notation, as it's sometimes called, this is a valid form to express a vector. You're writing it as a linear combination of the standard basis vectors I, j, and k. But there's no obligation to write it that way, and if you'd like to see it in a more familiar form, you can just collapse them into a single vector as follows. Just write it as the vector 2, -7, -6.